the buffer system, I'm going to basically walk through the Lab 5 analysis notes with you so you can follow along with the notes, and we're going to go through the different, how to calculate the pHs of the different solutions. That's the toughest part. Along the way, I might kind of make a couple comments on a few things. Let me see if I can't pull together a laser pointer. Okay. So I'm going to use a different buffer system than yours. I'm going to use carbonic acid and sodium carbonate. So in my specific example, I'm using 81.94 milliliters and 18.06 milliliters. I've given you the Ka for the acid system I'm going to use. However, remember, you did sodium acetate and acetic acid. So you're going to use whatever milliliters you were assigned that you actually made your buffer of 0.3 molar acetic acid. This is the Ka of it, and the sign of the sodium acetate, and that's going to be your system. So you're going to be able to shadow along with what I'm doing, but all the numbers are going to be different. Okay, let's first start off with some basic equations for the acid and the conjugate base. And remember, what is going on chemically? So weak acids partially dissociate in water. You know, they're going to form protons, which are really going to stick to water and be hydronium ions, and then they also make a conjugate base. So in my system of carbonic acid, when I add it to water, it makes hydronium ion, and here's my conjugate base. My conjugate base is this hydrogen carbonate ion. And I have H3O+, right? So this is going to be an acidic pH. I expect it's going to be less than 7 if I just had carbonic acid. Similarly, if I had a weak base, and I'm going to use this particular weak base, the conjugate base of this system, which is that hydrogen carbonate ion, it's going to make hydroxide ions and the conjugate acid, which is the weak acid we start with. So in this case, remember first, if I put sodium hydrogen carbonate in water, the first thing is it's going to fully dissociate, and it's going to make this hydrogen carbonate ion, which is my conjugate base. And then when that reacts with water, it makes hydroxide ion and the carbonic acid. Almost the reverse of the original situation. However, there's instead of having hydronium ion, we have hydroxide ions. So it's a little bit different. It's off by kW basically. But I'm making hydroxide ion. It's going to be a basic pH. I expect this to have a pH greater than 7. It might be pretty close to 7. It might be like 7.5 or 8 or 8.5, but it should be on the basic side. Okay, now I want to calculate the pH of a buffer. Remember, a buffer system is a weak acid with its conjugate base. I have to have 2 components in it. So this is a sort of specialty calculation. And it turns out that because of both of those, if I were to write out the ICE table, and you can see this in the notes that I did for the lab itself, if you do the derivation to get the Henderson-Hasselbalch equation, essentially it's just a Ka equation for the system, but realizing that I'm starting with initial concentrations of not just the acid or the conjugate base, but both. And I could go through it. It turns out if I assume X is pretty small and I have comparable amounts of both of them, I can make some nice assumptions. And I can say that pretty much I only need to know the initial conditions. That's really rare. Normally we need to know the equilibrium conditions. But my initial conditions under these specific conditions are close enough that I can get a pH from that. So I'll show you the Henderson-Hasselbalch equation in the end. But the problem is, so all I need to do is use that with the concentration of the conjugate base and the concentration of the weak acid, except when I actually mix them together, there's a dilution by mixing. So initial concentration is not the stock concentration of each substance. I mixed 81 milliliters of one thing with 18 milliliters of another, so now I have like 100 milliliters. So I've diluted that 81 milliliters down to 100. Similarly, I diluted the 18 milliliters down to 100. So I have to first calculate what is the diluted concentration, and then I can use the Henderson-Hasselbalch equation. So let's first do the dilution. So it's just M1V1 over V2. My 100 milliliters, I added the 81.94 and the 18.06. And here's it for the case of the acid. I'm using the 0.4 and the 81.94 milliliters. For the conjugate base, I'm using the 0.5 and the 18.06. So I get my concentrations. I also need the pKa value, which is just the negative log of the Ka value that was given. So in my case, it was 4.4 times 10 to the 17. Take the negative log of it, it's 6.36. Okay, so here This is my Henderson-Hasselbalch equation. The pH, which is what I'm trying to find, is the pKa, which I calculated, plus the log of the conjugate base concentration, that one's 0.0903, and over the concentration of the acid, that's 0.328. Calculate it out, and I get 5.80. Good. All right, what does that mean? Oops. Well, that doesn't mean anything, so we'll keep going on. All right, now what if I add a milliliter of acid to it? Strong acid in this case, HCl. I actually have two things that go on in this case. So I had a buffer, it was 5.80 pH, and now I'm going to add acid to it. Now, the fact that I add any volume means everything gets diluted. The 1 milliliters I added gets diluted to a total of 21 milliliters, and the 20 milliliter portions each get diluted to 21 milliliters. So I first have to deal with that dilution. So here's my M1V1V2 for the acid. Note that here I'm using the calculation I just figured out the dilution of mixing from the previous problem to make the buffer. There's 20 milliliters of 0.328 molar after I've mixed those. I mean, I had 100 milliliters, but I just take 20 milliliters out. It would be the same concentration. So this is the first dilution. Now I'm diluting it again. I'm using 21 on the bottom, and I get 0.312. Do the same for the others. Note that I also need to figure out what is the concentration of the HCl once I mixed it in. I diluted it from 1 milliliters to 21 milliliters, so that changes its concentration substantially. And now, the second thing that happens is that strong acid fully dissociates, and now it can react with the conjugate base that's present in the system. So some of my hydrogen carbonate ion is going to get reacted away by mixing with the H3O that I add, the hydronium ion I added, and and it's going to make the acid. Remember, if you go back to that original equation, the product of the conjugate base makes the weak acid. So that's going to increase by however much reacts. Now, I'm just going to use concentrations. Technically, it's mole, but if I assume I had 1 mole of it, it's going to end up working out by the time I'm said and done. So for the conjugate base, what it's reacting with, I'm going to subtract off how much acid I added. For the weak acid, I'm going to add, because it's going to, for every 1 that it reacts, of a conjugate base it reacts, it's going to make 1 weak acid. So that's going to increase it. So now I just figure out these new numbers. Once I have these adjusted concentrations, so they were first adjusted by dilution, then adjusted by reacting with the HCl, now I can plug them into Henderson-Hasselbalch. And I get 5.63. Note that 5.63 is really close to 5.80, but a little bit lower, meaning more acidic, which makes sense. 1, when I add strong acid, it should get more acidic. 2, a buffer system is designed to resist changes in pH. So I don't expect it to go drastically more acidic, but a little bit more acidic. So that's exactly what happened. Okay, what if we added a milliliter of sodium hydroxide? Note that we don't need to do this for the lab, but it's kind of the reverse thing with an extra little trick. I'm going to show it to you because you may need to do this in class. So similarly, 2 things happen. 1, the additional milliliter of volume dilutes everything a bit. 2, then the added hydroxide ion, remember it's a strong base, it's basically dissociating and making hydroxide ion, that can act with the weak acid in the reverse reaction of the conjugate base. So the weak acid plus the hydroxide makes hydrogen carbonate, that makes the conjugate base. So same idea, only my increases are going to go backwards. So I still have my original dilutions. Note that here it's the molarity of NaOH, but it was the same initial concentration, the same amount, so it ends up being the same number numerically. But for the conjugate base, that's what's being produced. So I'm going to add however much NaOH I had. Meanwhile, the conjugate acid is the thing that's reacting, so I'm going to subtract. So my numbers change a little bit, but it's the same idea. Okay, I plug it in, put them in my equation. So now my 0.1098 is on the top for my conjugate base. My 0.2282 is on the bottom. So these are here. I end up with 5.94. Remember, originally the buffer was 5.80. So this is slightly higher in pH, meaning more basic, which it should be because I added a strong base, but not much more basic because this is a buffer system and buffers are designed to resist changes in pH. So a little bit more basic. Okay, but what if I added water? Okay, I could add water to this system. All I really have to worry about is the dilution factor. I am going to dilute everything, but I'm not going to worry about a reaction. Water's not going to react with either component that's already there. So I just have to consider the effects of dilution. But we already had calculated those diluted volumes. The fact that I diluted it with water versus hydrochloric acid or sodium hydroxide doesn't change the dilution concentration. And now I put it in my Henderson-Hasselbalch. I get exactly the same number. Essentially, I diluted the conjugate at base, and I diluted the weak acid, but I diluted them by the same factor. And in a ratio, if I dilute this by the same amount as I dilute this, it doesn't change the ratio. So it's not going to change the pH. Adding water is not going to change the pH. Experimentally, you might see a slight difference, but it should be really close. Okay, now, let's say that was all what happens to buffer systems when you add acid and base. Let's switch to an unbuffered system, and the easiest unbuffered system is going to be water. So we're going to use water. You could actually do a calculation of the water, the pH of water, but I'm sure you've done that in class using the KW expression. It's 7, we all know. So we're not going to calculate that one. But we move on to solution number 6 and say, what if we had water, 20 milliliters of water instead of 20 milliliters of our buffer, and I added 1 milliliter of 0.5 molar HCl. In this case, there's only one component. So there isn't anything for the HCl to react with. And HCl is a strong acid, so it's going to completely dissociate. It's going to make a bunch of hydronium ion, and that hydronium ion has nothing to react with. So the pH is just the negative log of that hydronium ion concentration. So I just do a dilution and take the negative log of it. So here's my dilution. It's 0.0238 in this case. And then I take the negative log of it, and I get 1.62. We don't need the Henderson-Hasselbalch equation. This is not a system in equilibrium. It's a strong acid, fully dissociates. There's nothing else. There's no strong acids or weak acids in this system. So I don't need that Henderson-Hasselbalch equation. It wouldn't be useful. And now I can calculate it. Note that overall, I had started at 7. It did get more acidic, as it should when I add HCl, a strong acid, but it got much more acidic. It went from 7 to 1.62. That was a big jump. So this has a fairly large effect. There is no buffering. There is nothing for that hydronium ion to react with to sort of mitigate that change. And so we see a drastic change. Same thing if I added 0.5 molar sodium hydroxide to water. I dilute it, I got a dilution factor, but this is a little bit tricky. Remember, what I'm making there is hydroxide ion. Sodium hydroxide would dissociate into sodium ions and hydroxide ions. I want the pH, which has to do with the hydronium ion concentration. But we know that hydronium ion and hydroxide ion are in equilibrium, and so I can calculate one from the other. So you could either, I find it easier to take the negative log of the hydroxide ion concentration and get the POH. That was 1.62. And then use the factor that the pH and the POH add up to 14 to solve for what the pH would be. So note that this is also very basic, right? It went from 7 to 12. So it went basic, which it should because we added a strong base, but it was a big jump. Again, it's nothing, it's unbuffered. There's nothing for the hydroxide ion to react with. Okay, so the last two solutions are the pure weak acid and the pure conjugate base. For these, there's one component, but it's an equilibrium system. It's no longer a strong acid. It's a weak acid or a weak base. So we need to make an ice table and calculate what the concentrations would be from the Ka or the Kb value. So for the Ka, we already know it. This isn't too bad. I'm starting with 0.40 molar. I've got nothing else there. I change by X, and I end up with, I write out the Ka expression from the reaction. So the weak acid makes hydronium ion and conjugate base. Those are my products. They go on top. The weak acid goes on the bottom. Water is the liquid. We don't include it in Ka expressions. Now I plug in my numbers. I get X squared over 0.40 minus X. But here's where I say, yeah, but if X is small, which it should be, because this is a weak acid, it should only dissociate a little bit, right? That's what X represents. It's going to be close enough to 0.4 that I can just use that mathematically. Now I have an expression. I also know what the value of Ka is. So now I have this expression here. I can rearrange it and say that X, which is the hydronium ion concentration that I'm trying to find, is the square root of the Ka times the initial concentration. Get a number of 4.2 times 10 to the negative 4, take the negative log of it to get pH. I get 3.38. So note that this is acidic. This is the pH of a weak acid. It should be acidic. Won't be crazy acidic, but it should be acidic. And it depends what its actual pH is going to depend on what the Ka value for that particular weak acid is. The last one we have is the conjugate base. Very similar to the weak acid, but with a couple tricks. Remember now, since the only thing there is I need to consider a slightly different equation. This is now the carbonic acid with water makes hydronium ion. Oops, I think I have the wrong one here. Sorry. The pH of a conjugate base. Okay, same idea, but remember we've switched to using the conjugate base reaction. Note that when I switch it, I have slightly different things. First of all, I don't have hydronium ion in here. I have hydroxide ion. Also, I don't know the K value, the equilibrium constant for this reaction, but it is related to Kw and Ka. So I can solve for it. This is a Kb expression. I know Kw is 1 times 10 to the negative 14. I divide it by the Ka, and I get that, and it turns out to be 2.27 times 10 to the negative 8. So I find my Kb. The rest of it sets up the same. My Ka expression is a little different. Now my X is hydroxide ion, and I have weak acid on the top, conjugate base on the bottom. But the expression is pretty similar mathematically. Again, I use that weak acid approximation and say 0.50 minus X is basically 0.50. I solve for X, which is my hydroxide ion concentration, and I get a number, 1 times 10 to the negative 4. But remember, I want pH, which is based off the hydronium ion concentration. So once I have the hydroxide ion concentration, I have to find pOH by taking the negative log, 3.97, and then I have to subtract that from 14 because pH and pOH add up to 14, and I can find that it's 10.03. So that's how you're going to go through the calculations in this lab.